from first chapter unit and dimension, the second part or the mid part or major part of the chapter is a dimension. Dimension is for the basic physical quantities and the derived physical quantities. But here we calculate dimensions only for the derived physical quantities, because dimensions are nothing but the powers of the basic or fundamental physical quantities, because in a dimension we express all the physical quantities in terms of basic or fundamental physical quantities. For example, suppose I want to express a one derived physical quantity, that is a velocity. The formula for velocity is very simple. It is nothing but a displacement upon time. Here displacement is not my basic or fundamental physical quantity, but remember, displacement is nothing but it is a shortest distance, smallest distance measured from starting point, initial point, or the equilibrium point, or the mean point. Therefore, when you measure the displacement, we are measuring the distance, means we are measuring the length. Therefore, the velocity we also write, it is not physically correct, just we write for sake of our convenience, for understanding part only. Velocity means nothing but length upon time, or it's a distance upon time. Here length is symbolically expressed by L. Here there is only one power of length, therefore L raised to 1. At the denominator time is written, T stands for the time, there is only one power of time, there is only one term of the time, therefore L1 upon T raised to 1. So it will be simply written as a L raised to 1, T raised to minus 1. These are the dimensions of the velocity. It is very simple that the dimensions, the definition of dimension is like this. Dimensions of a physical quantity are defined as the powers. These are nothing but, dimensions are nothing but the powers to which any physical quantity means any derived quantity is expressed in terms of fundamental or basic. In other way, just we have to see that dimensions of derived quantities are nothing but the powers of fundamental physical quantities. Powers of fundamental physical quantities are nothing but the dimensions of physical quantity. Now we have to express dimensions in terms of mass, because mass is a fundamental or basic physical quantity. Length, symbol is L. T stands for the time. Then electric current, it will be expressed in some books, it is expressed in terms of I, or in some books it is expressed in terms of A. Here A is stands for the ampere, which is the SI unit of the electric current. Then sometime it is K. Kelvin is a unit of temperature. So fundamental physical quantities are mass, length, time, then the electric current, then the temperature, luminous intensity, and the amount of substance. These are the 7 fundamental physical quantities, and we write all the dimensions or all the powers of fundamental physical quantities always in a square bracket. Okay, means there are only two simple things. We can express any derived physical quantity in terms of fundamental or basic physical quantity, and the powers of that fundamental physical quantity are nothing but the dimensions. Dimensions are always written in a square bracket form. Now we see some examples of the dimensions of a physical quantity. Now the quantity is my area. Now if I say area is not a basic or fundamental physical quantity, so we have to write down the formula for area. Area is nothing but length into breadth. Here just we revise the 3 formulas for area. Suppose it is an area of rectangle, then a formula is a length into breadth. Suppose area of a square is there, then formula becomes area equals to length square. Suppose area sphere is given, then the area is given by 4 pi r square. If a circle is there, then area is given by a pi r square. Now here area is given by length into breadth. Suppose this is my one rectangle. This part is a length, this part is my breadth. We are measuring the breadth, means we are measuring again a length, that is my vertical length. So I am writing here length into again length, because breadth is nothing but my length. There are two terms, therefore I am also right, it's a length square. So the dimensions of area becomes m, that is no any term related to mass, therefore m raised to 0. There are only two terms related to length, so L raised to 2. There is no any term related to time, so T raised to 0. Again, we can express this in a square bracket, and we are getting the dimensions of area are m raised to 0, L raised to 2, and T raised to 0. Now see one more term, that is the volume. Take one more example. Second example is my volume. Now again volume is given by formula, it's a length into breadth multiplied by height. So length, breadth is again it's a one type of length, height is also a length, so it becomes a length cube. There are the three terms of the length, so it becomes an m raised to 0, no any term related to mass. There is L cube, length cube, therefore L raised to 3, and there is no any term related to time, so it becomes a T raised to 0. These are the dimensions of the volume. Now we see one more example, that is the density. Everyone know the formula for density. Formula for density is given by mass upon volume. Now I am expressing in terms of unit. This is a one more method, and it is most commonly used for a competitive exam, because it is very difficult to express every time the any derived quantity in terms of fundamental or basic physical quantity. Means suppose if I want to split or resolve this density in terms of fundamental, then it will be like this: mass as it is, volume again it's a length multiplied by breadth multiplied by height. So again I am writing in this way, it's a mass divided by length cube, and then I am getting the dimensions m raised to 1. There is only one term related to mass, L cube at the denominator, but when it comes to numerator, then it becomes a power becomes a negative or minus 3, and no any term related to time, so it becomes a T raised to 0. And again we express in terms of or in a square bracket form. But if I know the unit of density from the formula, mass is expressed in terms of kilogram, volume is expressed in terms of meter cube, so it will be very easy. Kg, kilogram is a unit of mass. There is only 1 kilogram, there is only 1 power of the kilogram, so it's a kg raised to 1, so m raised to 1. Then meter cube, meter is a unit of length, but it is present at the denominator. When it comes to numerator, then it becomes a minus 3, and there is no any term related to time, so it becomes a T raised to 0. And again we are getting directly the dimensions of density are m raised to 1, L raised to minus 3, and T raised to 0. Now see one more example. I think one by one we clearly understand the concept of dimensions and how you calculate the dimensions. Now next example is a force. Now basic formula for force equals to mass into acceleration. Again we can split this formula for force, because force is not a fundamental, it is a derived physical quantity. We express this force, it is a derived physical quantity in terms of fundamental. मीन्स जहाँ तक यहाँ फंडामेंटल फिजिकल क्वांटिटी नहीं आती, तब तक मेरा ये फोर्स का स्प्लिटिंग पूरा नहीं होने वाला. सो मास को मास एज इट इज रख दिया. acceleration means everyone know that it's a velocity upon time. Again mass को mass as it is, because it is a fundamental. velocity is nothing but displacement upon time, और ये पहले वाला time as it is, so it becomes like this. So again mass into displacement divided by time square. Again we split this mass as it is. Displacement is nothing but the shortest distance, means we are measuring the shortest length from mean position, divided by time square. Now you observe, all are the fundamental. Mass is a fundamental physical quantity, length is a fundamental physical quantity, time is a fundamental physical quantity. Means we can express, we can split, we can resolve, we can separate this derived physical quantity in terms of fundamental or basic physical quantity. So my formula for force, instead of mass into acceleration, this formula becomes force equals to mass into length upon time square. There is only one term related to mass, therefore m raised to 1. There is only one term related to length, so L raised to 1. There are two terms related to time, but which are in a denominator. When it comes to numerator, then it becomes a t raised to minus 2. So the formula for the dimensions of force becomes m raised to 1, L raised to 1, t raised to minus 2. What happens? Most of students says raised to. It is not raised to. L raised to 1, t raised to minus 2. It is not. It is a raised to. उसे लिफ्ट किया है, ऊपर लिया है, तो इसे raised to हम बोलेंगे. Now see one more trick to calculate the dimensions. The correct dimensions as it is. The formula for force is mass into acceleration. Mass is measured in terms of kilogram. Acceleration, unit of acceleration is a meter per second square. Everyone know that acceleration due to gravity of earth is a 9.8 meter per second square. So it is a very simple trick to remember the unit of acceleration, meter per second square. Now we have to write the dimensions. kg, there is only one term. Dimensions are always expressed in terms of mLt. Here kilogram, there is a unit of mass is a kilogram. There is only one term related to kilogram, so m raised to 1. There is only one power of meter. Meter is a unit of length, so L raised to 1. Second square, second is a SI unit of the time, and there is a second square. The power of second is a 2, but it is in a denominator. So when it comes to numerator, so it becomes a minus 2. Means from the unit we can also express the dimensions of the any derived physical quantity. Now we take one more example. Next example is a power. Formula for power. It will be very simple. Formula for power is a one formula, work per unit time. So I am writing here. Or the definition of power is like this: the rate at which work is performed is nothing but the power. So formula for power is a work done per unit time or work per unit time. Again, we can split this derived physical quantity in terms of fundamental or basic. Work is not a fundamental, so we split the work. Work is nothing but force multiplied by displacement. Remember, formula for work done is a force into displacement, not force into distance, divided by time as it is. Okay. Again, displacement means we are measuring the shortest length from mean position, so it's a fundamental. Time is a fundamental, but again question arises: force is not a fundamental, so again split the force. Force is nothing but mass into acceleration. Again, this term as it is, displacement divided by this time as it is. So I am writing here mass as it is. Acceleration, again acceleration means velocity upon time multiplied by displacement as it is upon time. Again velocity is not a fundamental, so we split this. So velocity is nothing but my displacement upon time divided by this time as it is multiplied by again displacement upon time. So again split this, mass into mass as it is, displacement divided by time square into displacement divided by time. Now you write the dimensions of power. There is only one term related to mass, so m raised to 1. there are two terms, displacement. Displacement means it's a shortest distance from mean position or it's a shortest length. There are two terms of displacement, so it becomes a L raised to 2 and all are in the numerator. Here time square and 1 time, so it becomes a time cube, but it is in numerator, it is in denominator, so when it comes in numerator it becomes a time raised to -3. So the dimensions of power becomes m raised to 1, L raised to 2, T raised to -3. But remember my friends, it's a traditional method. Now we see the shortcut. Formula for power is work done per unit time. Now you can split work means, again someone say sir work means force into displacement. Someone say that the work done per unit time, instead of this we can use energy per unit time, because definition of energy is like this: ability of body to do work, ability of body to perform work means energy. Means we can express energy, we can measure energy in terms of work. How much work is done by that object, that much amount of energy is present in that object. Therefore work and energy both are similar, both are analogous, both are unison terms. So power is nothing but energy per unit time, and everyone know formula for energy is a half of mv square, and time as it is a t is my time. So power becomes half mv square upon t. Remember that the dimensions are only for the physical quantities. 1 by 2 is not my physical quantity, it's a pure number. So when you calculate the dimensions, then we never write the dimensions of any number, any constant. Okay? So power, it's a 1 by 2 for only for formula it's a right, but when you measure the dimensions, when you calculate the dimensions, we require only mv square by t. Here mass, velocity. Velocity means again my displacement upon time, and there is a square divided by time. So my again formula becomes mass into square of displacement divided by square of time and whole divided by the time. Now I'm expressing unit. Mass is unit is a kilogram. Displacement meter square divided by time square, and this time when it comes in denominator it becomes a time cube, so it becomes a second cube. Now we write down kilogram is a unit of mass, m raised to 1. Meter square, it's a unit of length, so L raised to 2, because meter square is there, power of meter is a 2. And remember dimensions are nothing but the powers. And T raised to -3, here -3 because second cube is in a denominator. In this way we can calculate the dimensions of power. Now last one example, that is the V. In a statement of Ohm's law or mathematical form of Ohm's law, everyone know that V equals to IR. And so many number of students says in Ohm's law V is voltage. It's a totally wrong, my friends. V is a potential difference. Okay. Now we calculate the dimensions of resistance. Okay. So when R equals to, my formula becomes V by R. This is also my mathematical form of, one of the mathematical form of Ohm's law. So when I calculate the dimensions of resistance, see resistance symbol is R and formula is a V by R. Now we calculate the dimensions of resistance. Just we see the meaning of resistance. Resistance, it will be arises from the word to resist, and to resist means to oppose. Tendency of opposition of a body is called as a resistance, and in mechanics it is called as the inertia. Now resistance is given by V by R, but again we can split the derived physical quantity resistance in terms of fundamental or in terms of basic. Now it will be very difficult because V is my potential difference. How I split this potential difference in terms of basic or fundamental, that we have to see. And here electric current is also my SI or fundamental physical quantity. To calculate this dimensions of resistance or potential difference, we know the formula. One formula is that E equals to work done per unit charge. EMF equals to work done per unit charge. Sometimes when you study in detail second part of the physics, potential difference is nothing but work done per unit charge. So I am expressing this V instead of this work done per unit charge upon current. Here I am just be revising some terms, some basics. We clear this. Work done charge multiplied by current. Now what is the formula for current? Meaning of electric current. Electric current means flow of electrons per unit time. Flow of charge per unit time. So current is given by Q by T. Our aim is to calculate the dimensions of resistance, express this resistance in terms of fundamental, in terms of basic. So charge is not my basic. So express this charge in terms of current. So it becomes a Q equals to I multiplied by T. So formula becomes work done into I into T into I. So it becomes a work done into I square into T. Now see the denominator part is a totally fundamental or basic terms, current and the time. Now express this work done in terms of fundamental. Now it will be very simple. Work done. Again work done means force into displacement. So I am writing here force into displacement divided by I square into T. Force means what? Mass into or just mass into acceleration. So I am writing here mass into acceleration. S is my displacement divided by I means electric current, square of that multiplied by time. Just we are writing the units. Mass is measured in terms of kilogram. Acceleration unit is meter per second square. Displacement unit is meter divided by current, electric current ampere square because current square, and time is unit of time is second. Now again combine this kg as it is meter square, this divided by second square into second, it becomes a second cube multiplied by ampere square. Now we write down the definition, dimensions. Dimensions are always expressed in power of, in the powers of fundamental physical quantities. Here one more fundamental physical quantity is introduced, that is the electric current. Its SI unit is ampere. Now see here, kg is a unit of mass. There is only one term related to kg. Therefore kg, there is a mass raised to 1. Meter square, meter is a unit of length, power is a 2 because meter square, and which is in a numerator. Second cube, second is a unit of time and it is in denominator, so it becomes a -3. Ampere square, so a raised to -2 because it is in denominator. Now these are my dimensions of the resistance. Okay, I think everyone clear the concept of dimensions and everyone know or everyone easily understand how you calculate the dimensions of physical quantities. In next lecture we study what are the applications of dimensional analysis. Okay, thank you.